Okay, so one of the things that we have been able to do is we can take multiple derivatives. So suppose we have a relationship that we cannot write in a functional form. So tx cubed minus 3y squared equals 8. And what we want to be able to find is we want to find the second derivative. So our question is, can we find the second derivative of this? And so to do this, we need to take the first derivative. So we'll take this relationship here and we'll apply the first derivative to it with respect to x. Whoops, get my parenthesis right. We're taking it to the whole relationship. So this operator is applying to everything here. So we'll continue to apply the operation onto each term. And so this becomes 6x squared dx, because our variable was x, and we were taking, and of course we'll realize that'll become 1. This is 6y dy dx, and the derivative of a constant is 0. What we'll do then is we'll separate these, and I'm seeing this as 1 now because anything over itself is 1. And I'm going to solve for dy dx, and we get x squared over y. And so that's our first derivative. But we wanted the second derivative. Well, what we can then do is we can take the operator d dx to our result, and the application of this operator is going to give us d second derivative with respect to x. And what we need to do then is apply the derivative to this. And so we need to take the second derivative of we have y in the denominator, so we could use quotient rule. So we could look at this. Right, if we remember our quotient rule, let me put it over here. If I have some function of x over some function in x, which is not a bad way of doing this, then in the derivative of this is going to be the upstairs, the downstairs, times the derivative of the upstairs minus the upstairs times the derivative of the downstairs, and whatever the function is squared down below. Right. So we're going to use that to our advantage here. So what I want is I'm actually going to make my upstairs u x squared and my downstairs vy. Then I'm going to take the derivative with respect to x of u, which gives me 2x dx. And then I'm going to take my derivative of v, which is dy dx. And so I can say I'll take my downstairs, so I'm going to come down here. second derivative with respect to x of this is equal to the downstairs, which was y, times the derivative of the upstairs, 2x, minus the upstairs, x squared, minus the derivative of the downstairs, which is dy dx, all over the downstairs squared. And I'll clean this up. So I get 2xy minus x squared. Your book likes writing y prime for this. Because of how I do some things with parameterization in chapter 11 when you're in Calc 2, I like writing that all up there. And so we have our answer. But don't we know what this is? Didn't we do a lot of work to figure out what that was? So let's substitute in a little bit. So I guess can't really say our answer is completely done yet until we do the substitution back in. And I've been noticing as I've been grading people from different classes in my linear algebra and you guys, that you guys don't like fractions, and I'm trying. I think I'm going to give a lot more quizzes and exams where you don't have to use a calculator to get to fractions, because what I'm finding is people, instead of seeing something as a fourth or 3/4, they'll see it as 0.25, 0.75, and when we start getting fractions like this that we have to manipulate, we kind of lose some of the representations we can get, because we could look at this as 2xy over y squared minus x to the 4th over y cubed. And then in these extra y's cancel out, and we get 2xy minus x to the 4th over y cubed. Right, because you can divide a fraction on the negative sign here into the two terms that have the common denominator. Now, we do have an issue here that this derivative does not exist at 0. This is another example. This is very similar to the previous one, which I should have said also couldn't exist when y equals 0. The shape that this has is hyperbolic, so in nature, so it creates kind of two things that it's going across, but it comes together. It has an intersection point, this initial point at y equals 0. So when y equals 0, there's a flat point here. Let me draw better here. Let me come down and draw a little bit better. It's hyperbolic in nature. It's very similar to a hyperbolic. It's like a squashed hyperbolic. Right? A hyperbola is x squared minus y squared equals a constant. And this is very similar to that. The coefficients determine the slope of two lines that intersect. And so we have one line kind of coming in here steeply, and another line coming in narrowly. So it's a squashed hyperbola. And then in the curve itself, does some type of symmetrical turning like this. Let me get so it's kind of asymptotic to this line, pops up to a 0, and then goes asymptotic to this line, which is what hyperbolas do. But at these points, when y equals 0, we get vertical lines or an undefined slope. So this equation just does not work when y equals 0. And you're going to have some of those, which becomes important when we then have to solve in reverse and solve for the differentials, knowing that different answers might exist at y equals 0.